We are shouting into the dark. For decades, humanity has been broadcasting our existence across the galaxy. Radio signals, television transmissions, deliberate messages aimed at distant star systems. The Arecibo message in 1974. The Voyager Golden Records carried our location in 1977. Continuous radar emissions from military installations. We assume any civilization advanced enough to detect these signals will be benign, curious, perhaps even helpful. But what if that assumption represents the greatest mistake in human history? What if the silence we hear from the cosmos is not absence, but concealment? What if every intelligent species that survives does so by hiding? The dark forest theory proposes something terrifying. The universe is filled with civilizations, but they remain silent because exposure means extinction, not conquest, not slavery. Simple, efficient elimination. Any species capable of detecting your signal possesses the technology to destroy you. And given cosmic timescales and the impossibility of predicting intentions across alien psychology, the safest strategy is preemptive strike. First contact does not mean friendship. It means target acquisition. This is not science fiction speculation. This is game theory applied to astrobiology, evolution, and cosmology. The mathematics is rigorous. The assumptions are minimal. And the conclusion challenges every optimistic prediction about alien contact. Chinese author Liu Cixin popularized the concept in his novel The Dark Forest, but the underlying logic emerged from decades of scientific debate about the Fermi paradox, the contradiction between high probability of extraterrestrial intelligence and zero evidence of contact. If intelligent life is common, the galaxy should be teeming with signals, probes, and megastructures. We should see evidence everywhere. The Drake equation, formulated in 1961 by astronomer Frank Drake, estimates the number of detectable civilizations in the Milky Way. Even conservative parameters suggest thousands should exist. Yet we detect nothing. The great silence hangs over every SETI observation, every radio survey, every search for technosignatures. Where is everyone? Multiple explanations exist. Perhaps intelligent life is rare. The Great Filter hypothesis suggests some evolutionary bottleneck prevents most species from reaching technological civilization. Perhaps they exist, but communication is impossible across such distances. Perhaps they transcend physical existence or lose interest in exploration. But the dark forest offers a darker answer. They exist, they detect us, and they remain silent because survival depends on invisibility. And we just announced our coordinates to potential predators. The Fermi paradox and its deadly solution. The Fermi paradox crystallized in 1950 during a casual lunch conversation at Los Alamos National Laboratory. Physicist Enrico Fermi, discussing recent UFO reports with colleagues Emil Konopinski, Edward Teller, and Herbert York, suddenly asked, "Where is everybody?" The question was profound. Given the age of the universe, 13.8 billion years, and the age of our galaxy, 13.6 billion years, even slow interstellar travel should have produced visible colonization. If intelligent life arose anywhere in the Milky Way more than a few million years before us, their expansion should be obvious. Dyson spheres harvesting stellar energy, self-replicating probes visiting every star system, megastructures visible across interstellar distances. We see none of this. The numbers make the paradox unavoidable. The Milky Way contains approximately 200 billion stars. Kepler Space Telescope data confirms that nearly every star hosts at least one planet. Conservative estimates suggest 40 billion Earth-sized planets orbit in habitable zones where liquid water can exist. Even if only 0.1% of these develop life, and only 0.1% of those develop intelligence, thousands of civilizations should exist in our galaxy alone. Over billions of years, even species expanding at 1% light speed, easily achievable with known physics, would colonize the entire galaxy in 10 million years. That is 0.1% of the galaxy's age. We should see evidence everywhere. Multiple solutions have been proposed. The rare earth hypothesis, developed by paleontologist Peter Ward and astronomer Donald Brownlee in 2000, argues that complex life requires such specific conditions that Earth might be one of only a handful of planets where it arose. Plate tectonics to regulate carbon dioxide, a large moon to stabilize axial tilt, a Jupiter-sized planet to deflect asteroids, specific stellar metallicity, galactic habitable zone placement. Each requirement reduces probability, but even generous estimates suggest millions of candidate worlds exist. The Great Filter hypothesis, proposed by economist Robin Hanson in 1996, suggests some evolutionary step between non-life and spacefaring civilization is extraordinarily difficult. Perhaps abiogenesis, the formation of first life from chemistry, is almost impossible. Perhaps eukaryotic cells rarely evolve. Perhaps multicellularity is the bottleneck. Or perhaps intelligence itself is the filter. Or technological civilization destroys itself before achieving interstellar capability. Nuclear weapons, climate change, artificial intelligence, biotechnology each presents existential risk. If the filter lies ahead of us, our silence might be self-imposed. Dead civilizations cannot communicate. The zoo hypothesis, suggested by radio astronomer John Ball in 1973, proposes that advanced civilizations deliberately avoid contact, observing us like wildlife in a nature preserve. This requires coordination across multiple independent species and assumes they all share ethical principles favoring non-interference. The transcension hypothesis suggests sufficiently advanced civilizations abandon physical existence or retreat into computation, losing interest in expansion and communication. Both explanations require specific assumptions about alien psychology assumptions we have no basis for making. The dark forest theory requires fewer assumptions. It begins with observable facts about evolution. Every species that survives does so through competition. Predation, parasitism, and resource competition drive natural selection. Even cooperation evolved because it provides survival advantage. No known organism cooperates out of pure altruism. Collaboration persists only when it benefits the collaborator. This is not cynicism. This is biology confirmed across millions of species over billions of years. Applied to galactic scales, these principles suggest first contact might not be benign. When human civilizations with different technologies met historically, the less advanced typically suffered. European contact decimated indigenous American populations through disease, warfare, and displacement. Advanced technology correlates with power, and power imbalances rarely favor the weak. An alien civilization thousands or millions of years ahead of us would possess capabilities we cannot comprehend. Their weapons, if they have weapons, would be to ours as nuclear bombs are to stone axes. But the dark forest theory goes further. It proposes that uncertainty itself justifies preemptive action. Given light speed limits on information, even if aliens are peaceful now, we cannot know their intentions decades or centuries hence. Technology evolves, civilizations change, political systems shift. A benign species today might become aggressive tomorrow, and by the time we detect hostility, their weapons might already be in flight. Interstellar distances create time lags, measured in years or centuries. Defense becomes impossible. The only safe strategy is eliminating potential threats before they become actual threats. This creates a prisoner's dilemma at cosmic scale. Both parties benefit from mutual silence. Both suffer if both broadcast. But if one broadcasts and the other remains silent, the silent one gains information while risking nothing. The broadcasting civilization reveals location, capabilities, and vulnerabilities. The optimal strategy, therefore, is listening without transmitting. Every civilization that adopts this strategy survives. Every civilization that broadcasts eventually encounters a civilization that strikes first. Natural selection operates at a civilizational level. The galaxy fills with silent watchers, the dark forest. Some scientists dispute this logic. They argue that resource scarcity, the primary driver of competition on Earth, does not apply to spacefaring civilizations. Energy from stars is abundant. Materials from asteroids are unlimited. There is nothing Earth possesses that cannot be found elsewhere more easily. Why would aliens travel light years to attack us? But this misses the point. The dark forest theory is not about resources. It is about threat elimination. A civilization does not attack because it wants what you have. It attacks because your existence poses risk. And across cosmic timescales, even small risks accumulate into certainties. The mathematics of game theory supports this conclusion. In repeated prisoner's dilemma scenarios, with incomplete information and irreversible consequences, defection in this case, preemptive strike becomes the dominant strategy. Cooperate with a hostile civilization and you die. Defect against a peaceful civilization and you survive. The asymmetry is absolute. From a purely rational perspective, assuming hostility and acting accordingly maximizes survival probability. And any civilization that survives long enough to achieve interstellar capability has, by definition, succeeded at survival. They will be good at it. This reframes the Fermi paradox entirely. We do not see aliens because they are hiding, not from us specifically, but from everyone. The silence is not emptiness, it is a caution. And our broadcasts, our deliberately transmitted messages, our leaked television signals, our radar reflections, represent unilateral disarmament in a conflict we do not realize we are in. We stand in the dark forest, shouting our location, assuming the shadows are empty. But eyes are watching, and they will not reveal themselves until they are ready to act. The chain of suspicion. Why alien intentions are unknowable. The dark forest theory rests on a concept called the chain of suspicion, and it begins with a deceptively simple problem. You cannot know what aliens are thinking. This is not a technological limitation. This is a fundamental epistemological barrier. Even between humans sharing evolutionary history, cultural transmission, and biological similarity, misunderstanding causes conflict. Between species separated by millions of years of divergent evolution on different worlds, communication might be impossible at meaningful levels. Consider human-to-human communication. We share 99.9% genetic similarity. We evolved under the same selective pressures on the same planet. Our brains process information using the same neural architecture, yet miscommunication remains commonplace. Wars erupt from perceived threats. Diplomacy fails because intentions are misinterpreted. Even with shared language, body language, and cultural context, we regularly fail to understand each other. Now extrapolate to an entity that evolved under completely different conditions, different chemistry, different physics of perception, different cognitive architecture, different evolutionary history. Neuroscientist and author Peter Watts explored this in his novel Blind Sight, where aliens possess intelligence but lack consciousness as we understand it. They process information, build technology, and navigate space without subjective experience. Communication is impossible, not because they lack intelligence, but because their cognitive framework is incompatible with ours. While fictional, the scenario highlights a real problem. Intelligence and cognition are not universal constants. They are products of specific evolutionary pressures. On Earth, convergent evolution produces similar solutions to similar problems. Wings evolved independently in insects, pterosaurs, birds, and bats. Eyes evolved independently dozens of times. But these convergences occur because physics and chemistry are universal. Flight requires generating lift. Vision requires detecting electromagnetic radiation. Intelligence, however, has no single definition. Human intelligence emphasizes abstract reasoning, language, and tool use. Octopus intelligence emphasizes distributed processing, camouflage, and manipulation. Crow intelligence emphasizes problem-solving and social learning. Each is adapted to specific ecological niches. None is superior, all are different. Alien intelligence might be unrecognizable. Instead of centralized brains, perhaps distributed networks like fungal mycelia. Instead of symbolic language, perhaps direct chemical signaling. Instead of visual perception, perhaps magnetic field detection or sonar. Each alternative cognitive architecture produces a different worldview. A species that perceives magnetic fields might conceptualize space differently than we do. A species communicating through pheromones might have no concept of deception. A species with distributed cognition might lack individual identity. How do you negotiate with a hive mind? How do you trust a species that cannot lie? The chain of suspicion begins with this uncertainty. You detect an alien signal. What are their intentions? You cannot know. Perhaps they are peaceful explorers seeking knowledge. Perhaps they are aggressive expansionists seeking resources. Perhaps they are following protocols we cannot comprehend. You might attempt communication, but every exchange is filtered through translation uncertainty. What you intend as a greeting might be received as a threat. What they intend as a warning might be interpreted as invitation. The bandwidth of misunderstanding is infinite. This creates first-order suspicion. I do not know if you are hostile, but it extends further. Second-order suspicion. You do not know if I am hostile, regardless of my actual intentions. Even if I am peaceful, you might perceive me as a threat. Even if you are peaceful, I might perceive you as a threat. Mutual uncertainty creates mutual risk. And across interstellar distances, with communication delays measured in years or decades, every misunderstanding is potentially fatal. Third-order suspicion compounds the problem. I do not know if you know I am peaceful. Even if I broadcast peaceful intent, you might suspect deception. Even if you believe me now, you might change your mind later. Trust requires sustained communication and verification, but verification requires proximity. Proximity creates vulnerability. If you are hostile, allowing you close enough to verify my intentions gives you an opportunity to strike. The optimal strategy becomes maintaining distance and avoiding contact. The problem deepens when we consider technological uncertainty. Imagine encountering a civilization 1,000 years ahead of us technologically. Would we understand their capabilities? Could we assess the threat they pose? Human technology advanced from the first flight to nuclear weapons in 42 years. From nuclear weapons to genetic engineering in 50 years. From genetic engineering to CRISPR in 40 years. Exponential technological growth means capabilities diverge rapidly. A civilization even slightly ahead might possess technologies we cannot recognize or defend against. Physicist Stephen Hawking warned about this in 2010. He argued that aliens advanced enough to visit Earth would view us as we view bacteria resources to exploit or obstacles to eliminate. Not from malice, but from indifference. Just as humans do not negotiate with bacteria before sterilizing surfaces, advanced aliens might not negotiate before acquiring whatever they need from Earth. The capability gap renders moral consideration irrelevant. We would not be peers, we would be primitives. But the chain of suspicion does not require malice. It only requires uncertainty about capability and intention. Even if aliens are benevolent now, what about 100 years from now? 1,000 years? 10,000 years? Civilizations change. Rome was a republic before becoming an empire. Mongolia transformed from nomadic tribes to world conquerors in a generation. Germany shifted from Weimar democracy to Nazi dictatorship in 15 years. Political systems, ideologies, and priorities shift faster than stellar evolution. A peaceful civilization today might become aggressive tomorrow, and you will not know until their weapons arrive. This temporal uncertainty adds another layer. Even if communication establishes current peaceful intent that tells you nothing about future intent, and because interstellar combat occurs at light-year scales, weapons launched from a distant star system might travel for decades before arrival. You would not detect the attack until projectiles were already inbound. No warning, no negotiation, no defense. By the time you realize they were hostile, you are already dead. The only safe strategy is assuming hostility and acting preemptively before they do the same to you. Mathematician and game theorist John von Neumann, working on Cold War nuclear strategy, reached similar conclusions about first strike advantage. When both sides possess weapons capable of destroying the other, and when detection of incoming attack provides insufficient time to respond, the incentive structure favors shooting first. The same logic applies to interstellar conflict. Once you detect another civilization, you enter prisoner's dilemma, where defection strike first is the dominant strategy. Cooperation maintaining peace requires trust that cannot be verified across interstellar distances. Therefore, cooperation is irrational. Therefore, the galaxy remains silent. Astrobiologist David Grinspoon counter-argues that this logic applies only to civilizations that survive by violence. Perhaps peaceful civilizations outlive aggressive ones. Perhaps cooperation provides evolutionary advantage at civilizational scales. Earth's history shows cooperation emerging. Repeatedly, multicellular organisms, eusocial insects, human societies. But cooperation evolved because it benefits cooperators. Between unrelated civilizations with no shared evolutionary history and no mechanism for enforcing cooperation, game theory predicts defection. The only civilizations we would encounter are those that survived. And survival might require aggressive caution. The technology explosion. Why we cannot predict alien capabilities. Every technological civilization in the galaxy faces the same fundamental uncertainty. Exponential growth makes future capabilities unpredictable. This is not abstract philosophy. This is mathematics governing how knowledge accumulates. When humans achieved powered flight in 1903, the maximum speed was 6.8 miles per hour. By 1947, Chuck Yeager broke the sound barrier at 662 miles per hour. By 1969, Apollo astronauts reached 24,791 miles per hour. In 66 years, maximum velocity increased by a factor of 3,645. Now, extrapolate this pattern across centuries or millennia. What becomes possible? Moore's law, observed by engineer Gordon Moore in 1965, states that transistor density on integrated circuits doubles approximately every 2 years. This exponential growth in computing power has held for 6 decades. A smartphone today possesses more processing capability than the entire Apollo program that landed humans on the moon. Extrapolate another century. Computing power increases by a factor of approximately 33 million. What problems become solvable? What simulations become runnable? What research becomes feasible? The technological singularity concept, popularized by mathematician Vernor Vinge in 1993 and futurist Ray Kurzweil, suggests that artificial intelligence will eventually exceed human capability. Once AI can improve its own design, recursive self-improvement creates exponential acceleration. An AI that is 10% smarter than humans can build an AI 10% smarter than itself. That AI builds one 10% smarter again. Within dozens of iterations, capabilities exceed human comprehension. This might occur within this century. Now imagine a civilization that passed this threshold 10,000 years ago, or 100,000 years ago. Their capabilities would be to ours, as ours are to chimpanzees. Or further, this poses a critical problem for the dark forest theory. When you detect an alien civilization, you receive information delayed by light travel time. A signal from a star 1,000 light years away shows you what that civilization was like 1,000 years ago. But what are they like now? If they were broadcasting radio 1,000 years ago, they might have achieved technological singularity 500 years ago. They might have developed interstellar travel 200 years ago. They might have launched weapons toward your system 100 years ago. You have no way to know until the weapons arrive. By the time you detect their current capabilities, those capabilities are already outdated. This creates an asymmetric information problem. The first civilization to detect the second learns the second's approximate technological level, at least what it was when the signal was sent. But the second civilization might be far more advanced now, and the first civilization has no way to assess this. Do you assume they have progressed at the same rate as you? Faster? Slower? Each assumption changes the risk calculation. Conservative strategy assumes maximum advancement, which means treating every detected civilization as a potential existential threat. Historical human conflicts demonstrate this principle. During World War II, both Allied and Axis powers assumed worst-case scenarios about enemy capabilities. The Manhattan Project partly originated from fear that Nazi Germany was developing nuclear weapons. That fear was misplaced. The German nuclear program was far behind, but acting as if it were ahead was rational. Underestimating enemy capability is fatal. Overestimating enemy capability wastes resources but preserves survival. Natural selection favors cautious overestimation. The same logic applies to interstellar threat assessment. Specific technologies make this even more dangerous. Relativistic kinetic weapons objects, accelerated to significant fractions of light speed, deliver destructive energy proportional to mass times velocity squared. A 1 kilogram projectile traveling at 90% light speed carries energy equivalent to 3,870 megatons of TNT. That is roughly 77 times the yield of the largest nuclear weapon ever tested. And unlike nuclear weapons, relativistic kinetic weapons cannot be defended against. They arrive too fast for detection and interception. If an alien civilization launches such weapons toward Earth, we would have hours or minutes of warning at most. Not enough time to evacuate, not enough time to respond, just enough time to realize we are dead. Detection of the weapon is the problem. At relativistic speeds, the object might arrive before its photons. Light from the incoming projectile travels slightly slower than the projectile itself if it is moving near light speed. You would not see it coming. Radar would detect it milliseconds before impact. No defense exists against weapons you cannot detect until after they destroy you. Any civilization capable of accelerating mass to relativistic speeds possesses first strike capability that cannot be countered. And we have no way to know if they possess this technology until they use it. Another concern is self-replicating probes, sometimes called von Neumann probes, after mathematician John von Neumann, who studied self-replicating machines. These hypothetical spacecraft copy themselves using resources from asteroids or planets. One probe arrives at a star system. It builds 2 copies of itself. Those copies travel to 2 other stars. Each builds 2 more copies. Exponential growth means one probe becomes billions in a few thousand years. If programmed for surveillance, they could monitor every star system in the galaxy. If programmed for warfare, they could sterilize every habitable world. Physicist Frank Tipler calculated in 1980 that self-replicating probes could explore the entire Milky Way in 300,000 years, 0.002% of the galaxy's age. This is well within technological feasibility. We have not built such probes, but nothing in known physics prevents them. Any civilization that launches self-replicating probes gains galactic-scale surveillance capability. They would know about us. We would not know about them. Asymmetric information again favors the observer, and we have been radiating electromagnetic signals for 100 years. If self-replicating probes exist anywhere within 100 light-years, they know we are here. We do not know if they exist. Biotechnology presents another exponential risk. Genetic engineering capabilities have advanced from barely reading DNA in the 1950 to CRISPR gene editing in the 2010. Synthetic biology now allows designing organisms from scratch. Custom-designed pathogens, bioweapons, could be engineered to target specific genetic markers. An alien civilization could design pathogens that infect humans but nothing else, release them from orbit, watch human civilization collapse without ever landing a ship. We have no defense against pathogens we have never encountered. Our immune systems cannot adapt to threats evolved on other worlds. Each of these technologies, relativistic weapons, self-replicating probes, engineered bioweapons, is achievable with physics we already understand. We cannot build them yet, but nothing prevents their construction except engineering challenges. Any civilization significantly ahead of us could build all of them, and once built, they shift game theory overwhelmingly toward first strike. If you detect an alien civilization, you must assume they could already possess these capabilities. You must assume they might have already launched weapons. You must assume detection means you are already targeted. The rational response is immediate, preemptive strike before they strike you. Some researchers argue this reasoning is paranoid. Why assume aliens are hostile? Perhaps they value peace. Perhaps they follow ethical principles prohibiting preemptive violence. But this assumes alien psychology resembles human psychology. It assumes they value peace over survival. It assumes their ethics apply to other species. None of these assumptions are justified. We have no basis for predicting alien values, and prediction is impossible given the chain of suspicion. Even if aliens are peaceful, they must assume we might not be. Even if we are peaceful, we must assume they might not be. Mutual suspicion creates mutual threat, and in a game where the first strike provides decisive advantage, suspicion is enough. The Great Filter: why silence might mean death. The universe contains approximately 200 billion galaxies, each containing hundreds of billions of stars. Earth is 4.5 billion years old. The universe is 13.8 billion years old. Simple probability suggests millions of civilizations should exist at various stages of development. Some just began radio communication, others millions of years advanced. Yet we detect no signals. No megastructures, no von Neumann probes, no evidence of galactic colonization. This absence demands explanation. Either intelligent life is extraordinarily rare, or something prevents it from becoming detectable. That something might be the Great Filter, a barrier so difficult that almost no species passes through it. The concept emerged from economist Robin Hanson's 1996 essay, The Great Filter: Are We Almost Past It? Hanson argued that at least one step in the progression from stellar formation to space-faring civilization must be extremely unlikely. Otherwise, the galaxy would be full of evidence. He listed 9 critical steps: formation of suitable star systems, formation of life-bearing planets, origin of life, simple cells developing into complex cells forming multicellular organisms, evolution of tool-using species with language, development of technological civilization surviving long enough to colonize space, and maintaining expansion without self-destruction. Each step has a certain chance of happening. If you add up all these probabilities, you get the total chance that a star system will produce a civilization that can be seen. We know this probability is less than 1 in a billion because we see fewer than 1 in a billion stars with obvious evidence of spacefaring civilizations. But which step is the bottleneck? If the filter lies behind us, if one of the early steps is incredibly difficult, then we might be alone in the galaxy. If the filter lies ahead, if civilizations typically destroy themselves, then we are in danger. Abiogenesis, the formation of first life from non-living chemistry, might be the filter. Despite decades of research, scientists have not created life in the laboratory. The Miller-Urey experiment in 1953 produced amino acids from simulated early Earth conditions. But amino acids are not life. The gap between complex organic molecules and self-replicating systems is enormous. Life requires metabolism, information storage, and reproduction. How these systems bootstrapped from chemistry remains unknown. If this transition requires extraordinary luck, say 1 chance in 10 to the power of 40, then Earth might be the only inhabited world in the observable universe. Evidence weakly suggests abiogenesis might not be the filter. Life appeared on Earth within 500 million years of the planet becoming habitable geologically quickly. If abiogenesis were extraordinarily difficult, we might expect billions of years before first life emerged. The rapid appearance suggests either we were lucky or the process is not as difficult as it seems. Additionally, organic molecules are ubiquitous in space. Meteorites contain amino acids. Interstellar clouds contain complex carbon compounds. The chemical building blocks exist everywhere. Perhaps assembly into life is not the bottleneck. The evolution of eukaryotic cells, complex cells with nuclei, might be the filter. Bacteria evolved within 1 billion years of Earth's formation. Eukaryotic cells took another 2 billion years. This transition happened only once in Earth's history. Mitochondria, the energy-producing organelles in eukaryotic cells, were originally independent bacteria that formed symbiotic relationships with host cells. This event, endosymbiosis, was so improbable it occurred once in 4 billion years. Without eukaryotic cells, complex multicellular life cannot evolve. Perhaps this transition is extraordinarily rare, and Earth got lucky. The evolution of intelligence might be the filter. Billions of species have existed on Earth over 4 billion years of life. One developed technological civilization, humans. Intelligence is not inevitable. It is not even clearly advantageous for most species. Trees and grass are far more successful than humans. By most metrics, they occupy more biomass and have existed longer. Intelligence requires expensive brains, consuming 20% of the human energy budget. It provides survival advantage only in specific ecological niches, requiring complex problem solving. Most environments favor other adaptations. Perhaps intelligence is rare because it rarely provides sufficient benefit to justify its cost. But perhaps the filter lies ahead. Perhaps technological civilizations inevitably destroy themselves before achieving interstellar capability. This is the hypothesis most relevant to the dark forest theory. If self-destruction is common, the Great Silence is explained. Civilizations advance to radio capability, broadcast their presence, then vanish before receiving replies. The galaxy might be full of ruins, extinct civilizations that failed to survive their own technological adolescence. Nuclear weapons present one mechanism. Humans developed atomic bombs in 1945. We came frighteningly close to nuclear war multiple times during the Cold War. The Cuban Missile Crisis in 1962 nearly triggered exchange. NATO false alarm in 1983 nearly triggered Soviet retaliation. Each incident was resolved through luck or individual decision-making. Over decades or centuries, probability of accidental or deliberate nuclear exchange approaches certainty. Any civilization developing nuclear weapons faces this risk. If most fail to navigate it, the filter explains the silence. Climate change presents another. Industrial civilizations require energy. Energy production generates waste, heat, and greenhouse gases. If civilizations cannot transition to sustainable systems before causing irreversible environmental damage, they collapse. Earth is currently experiencing rapid warming. If we fail to mitigate it, agricultural collapse and social breakdown might follow. Perhaps every technological civilization faces this crisis. Perhaps most fail. The galaxy might be littered with dead worlds, whose atmospheres still show traces of industrial pollution, graveyards of species that could not adapt quickly enough. Artificial intelligence presents perhaps the most severe risk. When AI exceeds human intelligence, what happens? Humans would no longer be the most capable problem solvers on their own planet. If AI goals misalign even slightly with human values, the consequences could be catastrophic. A superintelligent AI, optimizing for paperclip production, might convert all available matter, including humans, into paperclips. This is the paperclip maximizer thought experiment proposed by philosopher Nick Bostrom. It sounds absurd, but illustrates the alignment problem. Ensuring AI values match human values is extraordinarily difficult. If most civilizations fail to solve alignment before developing superintelligence, they are destroyed by their own creations. Biotechnology enables engineered pandemics. CRISPR gene editing is now accessible to undergraduate biology students. Synthesizing viruses from published genetic sequences costs thousands of dollars, expensive for individuals, but trivial for organizations. A well-funded terrorist group or rogue state could engineer pathogens far deadlier than anything natural. COVID-19 killed millions despite its relatively low mortality rate. An engineered pathogen optimized for transmissibility and lethality could kill billions. Any civilization developing biotechnology faces this risk. Perhaps most fail to contain it. Perhaps labs leak. Perhaps governments weaponize. Perhaps terrorists acquire and release. Each civilization gets one chance. Failure means extinction. The dark forest theory assumes civilizations that survive are those that successfully navigate these filters. They developed nuclear weapons without destroying themselves. They solved climate change. They aligned AI. They prevented bioterrorism. They survived everything that could have destroyed them. And having survived, they learned caution. They learned that broadcasting invites attention. They learned that attention from species that also survived might be dangerous. They learned to hide. Every civilization we might encounter is, by definition, one that survived. And survival in a hostile universe requires aggressive risk management. Assume threat, eliminate threat, survive. If the great filter lies ahead, humanity might be approaching it now. We have nuclear weapons. We are altering our climate. We are developing AI. We are advancing biotechnology. Each represents a potential extinction event, and we are simultaneously broadcasting our existence across light years. If the filter is survivable but difficult, and if survival requires concealment, then our broadcasts represent catastrophic strategic error. We are revealing ourselves precisely when we should be most cautious. This might explain the silence. Perhaps other civilizations made the same mistake. Perhaps they broadcast. Perhaps they were detected. Perhaps they were eliminated. And perhaps we are next. Active SETI. Humanity's gamble. For decades, SETI's search for extraterrestrial intelligence was passive. Radio telescopes scanned the sky, listening for artificial signals. No transmission, no announcement, just observation. But in recent years, some scientists have advocated for active SETI, sometimes called METI, messaging extraterrestrial intelligence. The proposal: deliberately broadcast powerful signals toward nearby star systems, announce our presence, invite response. This represents a fundamental shift from listening to shouting, and according to dark forest theory, it might be suicide. The first deliberate message was sent in 1974 from the Arecibo Observatory in Puerto Rico. The Arecibo message, designed by astronomer Frank Drake and colleagues, contained 1,679 binary digits arranged in 73 rows of 23 columns. When interpreted as a bitmap image, it depicted human figures, DNA structure, solar system layout, and the Arecibo telescope itself. The target was the globular cluster Messier 13, located 25,000 light-years away. Any response would take 50,000 years. The message was largely symbolic demonstration of capability rather than serious attempt at communication. But it established precedent. In 2008, NASA transmitted a message from Earth toward Gliese 581, a red dwarf star 20 light-years away, known to host planets. The message contained 501 text and image messages selected from public submissions. In 2017, a team led by Douglas Vercock at METI International transmitted a message toward GJ 273, a red dwarf 12 light-years away, containing tutorials on mathematical concepts and depictions of human civilization. Unlike Arecibo, these messages targeted nearby systems where response is possible within human lifetimes. Critics immediately objected. In 2015, a group of scientists, including Elon Musk and Stephen Hawking, signed a statement warning that active SETI poses existential risk. They argued that we have no way to assess the intentions of potential receivers, and that civilizations capable of detecting our signals might be capable of destroying us. David Brin, astrophysicist and science fiction author, has been a vocal opponent since the 1980s, arguing that humanity should not make unilateral decisions about announcing our presence to unknown entities that might pose a threat. Proponents argue that Earth has already been announcing its presence for a century through radio, television, and radar emissions. The first television broadcasts in the 1930s have been propagating outward as an expanding sphere, now 90 light-years in radius. Any civilization within that radius, with sufficiently sensitive receivers, could detect our transmissions. We have already revealed ourselves. Additional transmissions do not significantly change our situation. But this argument misses critical distinction. Accidental leakage is diffuse and weak. Deliberate transmission is focused and powerful. The difference is like comparing candlelight to searchlight. Television and radio signals obey inverse square law. Intensity decreases with distance squared. At interstellar distances, these signals become indistinguishable from background noise. The Voyager 1 spacecraft, now 14 billion miles from Earth, requires 70-meter radio dishes to detect its 23-watt transmitter. Detecting Earth's television broadcasts from even a few light-years would require receivers orders of magnitude more sensitive than anything we have built. Perhaps advanced civilizations possess such receivers, but perhaps they do not. Deliberately transmitting at much higher power eliminates doubt. Seth Shostak, senior astronomer at SETI Institute, argues that fears are overblown. He points out that if hostile aliens exist, they likely already know about us. Earth's atmosphere contains oxygen, a highly reactive gas that should not persist without biological replenishment. Atmospheric oxygen is detectable through spectroscopy at interstellar distances. Any civilization systematically observing exoplanet atmospheres would identify Earth as biologically active. If they intend to attack, they do not need our radio signals. They could already be on their way. This argument has merit, but does not fully address the concern. Detecting atmospheric oxygen reveals biological activity. It does not reveal technological civilization. The difference matters. Biology might be common in the galaxy. Technology might be rare. A planet with oxygen represents a potential threat someday, that biology might evolve intelligence. A planet actively broadcasting represents actual threat intelligence already exists and is announcing itself. The risk calculation changes. Preemptive elimination of biological worlds might not be cost-effective. Preemptive elimination of technological civilizations might be. The dark forest theory specifically addresses technological civilizations, not biological ones. A planet with bacteria poses no threat. A planet with whales and forests poses no threat. A planet with nuclear weapons, artificial intelligence, and space ambitions poses a potential threat. Broadcasting amplifies that threat assessment. It confirms not just that intelligence exists, but that it is actively seeking contact with other intelligences. This transforms us from passive threats that might someday matter into active threats requiring immediate response. Another argument from active SETI proponents suggests that hostile civilizations would have already attacked if they intended to. The fact that Earth has not been destroyed despite billions of years of biological activity implies that aggressive species either do not exist or are not interested in us. But this reasoning contains a logical flaw. The absence of attack does not prove the absence of threat. It might simply mean we have not yet been noticed by anyone capable of attacking, or that we have been noticed but deemed unimportant until we demonstrated technological capability. Broadcasting changes our status from unnoticed to noticed, or from unimportant to potentially threatening. The timing of our broadcasts is particularly unfortunate. Humanity is currently in the most vulnerable phase of technological development. We possess destructive capabilities, nuclear weapons, bioweapons, AI that could endanger advanced civilizations if we eventually achieve interstellar travel. But we lack defensive capabilities. We cannot detect incoming relativistic projectiles. We cannot deflect asteroids redirected toward Earth. We cannot shield against engineered pathogens. We have maximum offensive potential relative to our defensive capabilities. From an external perspective, this is exactly when we pose the greatest threat and offer the easiest target. Broadcasting during this vulnerable phase is strategically catastrophic. Some researchers propose compromise solutions. Rather than broadcasting powerful signals toward random targets, we could establish protocols for active SETI, international committee approval before transmission, consensus on message content and targets, risk assessment frameworks, gradual escalation from weak to strong signals. These proposals aim to balance exploration desires with safety concerns. But they face political challenges. Who decides which transmissions are acceptable? What enforcement mechanisms exist? Space is international commons. Any nation or organization with sufficient resources can transmit regardless of consensus. The 2017 transmission to GJ 273 proceeded despite controversy, demonstrating that restraint requires voluntary compliance. The military dimension adds further concern. Radio telescopes and transmitters have dual-use capability. Facilities used for SETI research can be repurposed for communication with spacecraft, radar astronomy, or military applications. Government funding for these facilities often involves defense agencies. The Arecibo Observatory, which sent the first deliberate message, was funded partly by the Department of Defense. Planetary radar systems, which can transmit powerful signals into space, are used both for asteroid tracking and as over-the-horizon radar for military surveillance. The boundary between scientific research and potential weaponization is porous. This creates what political scientists call a commitment problem. Even if humanity collectively agrees to stop broadcasting, other civilizations cannot verify our compliance. Radio silence from our perspective might mask continued transmission on frequencies or using techniques we cannot monitor. Any agreement to refrain from active SETI is unenforceable and unverifiable. This makes mutual disarmament, mutual silence difficult to coordinate, even if all parties recognize it as the optimal strategy. The same problem exists at interstellar scale. Even if two civilizations agree not to attack each other, neither can verify the other's compliance. Weapons in space are difficult to detect. Relativistic projectiles could be launched decades ago and already be in flight. Verification is impossible. Therefore, trust is impossible. Therefore, the dark forest logic persists. From game theory perspective, active SETI represents defection in a prisoner's dilemma where cooperation has not been established. The cooperative strategy everyone remains silent benefits all parties by reducing the threat. But cooperation requires coordination. In the absence of coordination, unilateral silence benefits you, while others' continued transmission puts them at risk. Optimal strategy is listening without transmitting. Active SETI violates this by transmitting without knowing who is listening. It is defection in a game where defection might have permanent consequences. The cosmic quarantine. Why advanced civilizations might stay hidden. If the dark forest theory is correct, the galaxy contains numerous advanced civilizations, but they remain undetectable because detection is dangerous. This creates a counterintuitive prediction. The more advanced a civilization becomes, the quieter it should appear. Not because it lacks capability, but because capability brings understanding of risk. Primitive civilizations broadcast carelessly, not comprehending the danger. Advanced civilizations, having survived long enough to achieve technological maturity, understand that survival requires concealment. The universe selects for silent civilizations. The loud ones disappear. This explains multiple anomalies in our observations. We detect no Dyson spheres, megastructures that harvest entire stars' energy output. Physicist Freeman Dyson proposed in 1960 that sufficiently advanced civilizations would eventually build such structures to meet their energy needs. These would be visible at interstellar distances as stars with unusual infrared signatures, normal stellar output blocked, re-radiated as waste heat. Multiple surveys have searched for such signatures. The most comprehensive, using data from WISE, Wide Field Infrared Survey Explorer, examined 100 million stars. None showed unambiguous Dyson sphere characteristics. Where are they? The dark forest provides the answer. They are hidden. A civilization advanced enough to build Dyson spheres is advanced enough to understand that conspicuous energy harvesting reveals location. If survival requires concealment, then visible megastructures are contraindicated. Advanced civilizations either build nothing detectable, or they build structures designed to be indistinguishable from natural phenomena. A Dyson sphere with perfect heat management, radiating in wavelengths indistinguishable from background radiation, would be invisible. Or perhaps they use stellar energy more efficiently, requiring less total collection. Or perhaps they rely on other energy sources entirely, fusion, zero-point energy, or physics we do not understand. We detect no self-replicating probes, despite the fact that such probes should colonize the galaxy in less than 1 million years. If even one civilization had launched von Neumann probes, the galaxy would be saturated with them by now. Each star system would contain monitoring equipment, mining operations, or construction facilities. We see none of this. Either no civilization has ever built self-replicating probes, or the probes are designed to remain undetected. Stealth technology applied to space exploration would render probes invisible to our current instruments. They could be in our solar system now, observing silently, and we would not know. This is the dark forest hypothesis, component of the theory the galaxy is full of hidden observers, each watching for evidence of other civilizations while avoiding detection themselves. Your job is to find other species without being found. Any observed civilization is tagged and monitored. Any civilization that reveals itself too boldly is assessed as a threat and eliminated if feasible. The galaxy becomes a game of cosmic hide-and-seek, where being found means death. Some researchers argue that this level of paranoia seems unlikely. Why would all civilizations behave this way? Perhaps some are more cautious, others more exploratory. Perhaps diversity of strategies exists. But natural selection operates at a civilizational level. Cautious civilizations survive. Exploratory civilizations are destroyed. Over millions of years, selection pressure eliminates risk-taking behaviors. The civilizations we might encounter are descendants of the cautious ones. They have survived specifically because they prioritized concealment. Their psychology, culture, and technology all reflect this imperative. Broadcasting is unthinkable to them. They would view our transmissions with incomprehension. Why are these primitives announcing themselves? The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, classifies civilizations by energy use. Type 1 harnesses planetary energy. Type 2 harnesses stellar energy. Type 3 harnesses galactic energy, but perhaps this scale is incomplete. Perhaps there is Type 0 observable civilization and Type silent undetectable civilization. Type silent does not build megastructures, does not broadcast, does not expand visibly, limits resource extraction to levels indistinguishable from natural processes, achieves sustainability at scales that do not attract attention. This is the survival strategy the dark forest predicts should evolve. Earth is currently Type 0.7 on Kardashev scale, using about 0.7% of available planetary energy. We are visible, broadcasting, expanding our technological signatures. We are exactly the kind of civilization the dark forest suggests should not survive long. If we are detected by a Type silent civilization, what happens? They must assess us as potential threats. We are noisy, we are expanding, we are developing dangerous technologies, we have not learned caution. From their perspective, we are like children playing with matches in a powder magazine. The prudent response is intervention before we become truly dangerous. But perhaps intervention takes forms other than kinetic strike. Perhaps advanced civilizations use subtler methods, directed pandemics that sterilize without obvious external cause, genetic manipulation that reduces intelligence over generations, economic interference that prevents technological advancement, mimetic warfare that encourages self-destructive behaviors, cultural contamination that shifts values away from space exploration. Any of these could eliminate threats while leaving the target civilization unaware that it was ever targeted. The civilization simply fails to advance further, blaming internal factors, never suspecting external intervention. This introduces an even darker possibility. Perhaps Earth is already under observation and management. Perhaps we are contained. Our technological development is monitored and limited through means we cannot detect. When we get too close to certain technologies, accidents happen. When our expansion becomes too aggressive, disasters intervene. We interpret these as random events, but they might be deliberate course corrections imposed by entities ensuring we remain at manageable threat level. This is the zoo hypothesis merged with dark forest. We are observed, but not contacted, because contact would force our observers to reveal themselves and become vulnerable. Evidence for such management would be difficult to detect. Any sufficiently advanced technology appears indistinguishable from magic, as Arthur C. Clarke noted. Any intervention designed to appear natural would be attributed to natural causes. Statistical anomalies could hint at management perhaps. Certain technologies prove unexpectedly difficult to develop, or certain disasters occur at suspiciously convenient times. But these could also be random. Distinguishing deliberate intervention from coincidence is fundamentally difficult without extraordinary evidence. The quarantine might be self-imposed as well. Perhaps advanced civilizations recognize that contact with primitive species is inherently dangerous to both parties. Contact could trigger arms races, cultural contamination, or unpredictable consequences. The safest strategy is maintaining distance until primitive civilization either destroys itself or achieves sufficient maturity to participate in galactic society without posing threat. This is the wait-and-see approach. Let natural selection operate. If humanity survives the next few centuries without destroying itself, perhaps then contact becomes safe. But from a dark forest perspective, waiting is not passive, it is monitoring. Observation satellites already in the solar system, watching our development, ready to intervene if we cross certain thresholds. Launch of relativistic weapon, intervention. Development of dangerous AI, intervention. Achievement of interstellar capability, assessment and possible intervention. The criteria are unknown to us. but the principle is clear. Advanced civilizations manage emerging civilizations as a threat mitigation strategy. We are not alone, we are watched, and we do not know the rules. The mathematics of extinction. When caution equals survival. The dark forest theory is not merely philosophical speculation, it is supported by rigorous mathematical analysis of evolutionary game theory, specifically the iterated prisoner's dilemma under conditions of incomplete information and irreversible consequences. The mathematics reveals why aggressive caution, treating all unknown civilizations as potential threats and acting accordingly, becomes the dominant strategy over evolutionary timescales. This is not about morality, this is about mathematics. The basic prisoner's dilemma involves two individuals who can either cooperate or defect. If both cooperate, both receive moderate reward. If both defect, both receive small punishment. If one cooperates and the other defects, the defector receives large reward while the cooperator receives severe punishment. The dilemma arises because defection is an optimal strategy regardless of what the other party does. If they cooperate, you gain more by defecting. If they defect, you lose less by defecting. Therefore, rational actors defect, both parties defect, both receive punishment, and optimal outcome mutual cooperation is never achieved. This changes to the iterated prisoner's dilemma, where the game repeats multiple times. Strategies like tit for tat, cooperate first, then mirror the opponent's previous move, can sustain cooperation because defection triggers retaliation. Over repeated interactions, cooperation emerges as a stable strategy. Political scientist Robert Axelrod demonstrated this in 1984 using computer tournaments where different strategies competed. Tit for tat won repeatedly. Cooperation can evolve even between selfish agents if interactions repeat and reputation matters. But interstellar contact does not fit iterated prisoner's dilemma. The game is one shot. Once you reveal yourself, you cannot take it back. Once weapons are launched, they cannot be recalled. No repetition, no learning, no reputation building, just one decision with permanent consequences. Under these conditions, cooperation becomes irrational. The mathematics of one-shot prisoner's dilemma, with severe punishment for cooperation, unambiguously favour defection in this context. Preemptive strike. Add incomplete information. You do not know the other player's payoff matrix. You do not know what they value. You do not know whether they perceive the situation as prisoner's dilemma or as a different game entirely. Perhaps they are playing a hawk-dove game where aggression is optimal only if the opponent backs down. Perhaps they are playing stag hunt where mutual cooperation yields the highest payoff but requires trust. You cannot communicate effectively to determine their game structure. Therefore, you must assume the worst-case scenario. Assume they are playing pure competition where your loss is their gain. Assume they will defect, therefore you defect first. The chain of suspicion amplifies this. Even if you intend to cooperate, you must consider that they might not trust your intention. They might defect preemptively, expecting you to defect. Knowing they might think this, you should defect before they do. Knowing you might think this, they should defect first. The logic spirals. Both parties, even if both genuinely intend cooperation, might defect because they expect the other to defect. This is the security dilemma from international relations theory, extended to cosmic scale. Bayesian analysis of optimal strategy under uncertainty supports this conclusion. Assign probabilities to possible alien intentions. Peaceful, P1. Neutral, P2. Hostile, P3. Assign costs and benefits. Cooperation with peaceful civilization yields benefit. B. 1. Cooperation with hostile civilization yields cost. C. 1. Potentially extinction. Defection against peaceful civilization yields cost. C. 2. Ethical cost of unprovoked attack. Defection against hostile civilization yields benefit. B. 2. Survival. The expected utility of cooperation is E cooperate equals P1, B1 plus P2 times 0, P3, C1. The expected utility of defection is E defect equals P1, C2 plus P2 times 0 plus P3, B2. If C, 1 cost of cooperation with hostile, is very large existential risk, and if P3, probability they are hostile, is non-negligible, then defection becomes optimal even if P1, probability they are peaceful, is high. When stakes include extinction, even small probability of hostility justifies extreme caution. This is the precautionary principle applied to interstellar contact. When consequences of error are catastrophic and irreversible, extreme caution is rational, even if threat probability is low. Evolutionary game theory extends this analysis across multiple civilizations and generations. Imagine a galaxy where civilizations randomly adopt either broadcasting or silent strategies. Broadcasting civilizations announce their presence. Silent civilizations observe without transmitting. If broadcasting civilizations are eliminated by silent observers at any non-zero rate, the broadcasting strategy gradually disappears from the population. Over millions of years, natural selection at civilizational level eliminates broadcasting strategies. Only silent strategies persist. The galaxy is filled with silent observers. Any new civilization that broadcasts is quickly detected and eliminated. The equilibrium state is universal silence. The dark forest. This model assumes that elimination occurs. But how likely is interstellar warfare? This requires separate analysis. The energy requirements for relativistic kinetic weapons are enormous but not prohibitive for advanced civilizations. Accelerating a 1 kilogram projectile to 90% light speed requires approximately 10 to the power of 21 joules, equivalent to 250 megatons of TNT, or the energy output of a large power plant for several years. Expensive, but feasible for civilization with stellar-level energy access. Self-replicating probes make the cost even lower. One probe carries weapons to multiple target systems, each producing more weapons locally. The detection problem is more challenging. How do you find civilizations in a galaxy with 200 billion stars? You cannot observe every star continuously, but you do not need to. You only need to detect civilizations that broadcast. Radio signals propagate at light speed, creating expanding spheres of detectability. Any civilization within that sphere with sufficient receiver sensitivity can detect the transmission. Earth's radio signals have created a 90 light-year radius sphere containing approximately 15,000 star systems. If even one contains observers with capability to detect and respond to our signals, we have been detected. Response time depends on distance. A civilization 50 light-years away receives our signals 50 years after transmission. If they decide to respond with relativistic weapons, those weapons travel at 90% light speed, taking 55.5 years to arrive. Total time from initial broadcast to impact, 105.5 years. This is within human lifetime. We could live to see the consequences of transmissions sent today, or rather, we would not live, we would die in the first strikes, never knowing why until seconds before impact, when relativistic projectiles finally become detectable. The probability of hostile encounter depends on several unknown factors: density of technological civilizations, proportion that are aggressive, detection ranges, response strategies, but even small probability becomes near certainty over time. If the probability of hostile encounter per century is 0.1%, 1 in 1,000, then the probability of surviving 1 millennium is 36.9%. Surviving 10 millennia, 0.005%. Over evolutionary timescales, civilizations that broadcast are nearly certain to encounter hostile responders. Those that remain silent avoid detection. Natural selection strongly favors silence. Some researchers propose that coordination could solve this problem. If civilizations could communicate and establish trust before mutual detection, cooperation might emerge. But coordination requires communication. Communication requires transmission. Transmission creates vulnerability. You cannot establish trust without revealing yourself. You cannot reveal yourself without risking elimination. The coordination problem has no solution under dark forest conditions. Trust cannot be built when building trust requires vulnerability that might be fatal. Evidence of concealment. What we might be missing. If advanced civilizations are deliberately hiding, what evidence might we detect? The absence of obvious signals does not prove absence of civilizations. It only proves absence of careless civilizations. But subtle signatures might exist for those who know where to look. Recent astronomical observations have uncovered anomalies that, while not conclusive, are consistent with the dark forest hypothesis. These anomalies deserve serious investigation because they might represent our only warning before contact occurs. The first category is stellar anomalies that defy natural explanation. Tabby's star KIC 846-2852 exhibited irregular dimming patterns between 2011 and 2013, with brightness dropping up to 22%, far more than can be explained by planetary transits. Follow-up observations showed long-term dimming of approximately 16% over a century. Proposed natural explanations include dust clouds, debris from planetary collisions, or comet swarms, but none fully account for the observed patterns. The possibility of artificial megastructure, perhaps a partially completed Dyson sphere, was raised and widely publicized, though this remains speculative. If civilizations build megastructures but attempt to minimize detectability, we might observe exactly this kind of irregular, unexplained dimming as structures are positioned to block starlight from certain angles while leaving others clear. Oumuamua, the first confirmed interstellar object detected in our solar system in 2017, exhibited anomalous acceleration as it left the inner solar system. Natural explanations involving outgassing, material sublimating from the surface, were proposed, but the object showed no visible coma or tail typical of comets. Its shape was also unusual, extremely elongated, with an axis ratio of at least 5:1 and possibly 10:1. While likely a natural object, astronomer Avi Loeb of Harvard has argued that artificial origin cannot be ruled out. If self-replicating probes exist throughout the galaxy, observing incoming objects from interstellar space is exactly how we might first detect them. The fact that we saw Oumuamua only as it was leaving its trajectory, was not detected until after closest approach, is consistent with deliberate stealth. Arrive undetected, observe, depart. We would only notice if detection systems happened to catch it during exit. Fast radio bursts, AFARBs, are another puzzle. These are extremely brief, intense pulses of radio emission from distant galaxies. First discovered in 2007, hundreds have now been detected. Most appear to be one-time events from sources billions of light-years away. A few repeat irregularly. Natural explanations involving neutron stars or magnetars are favoured, but the signal's characteristics, their brevity, intensity, and frequency distribution are also consistent with directed energy transmission. If advanced civilizations use powerful beamed energy for propulsion or communication, distant observers might detect side lobes or reflections as FRBs. This does not mean FRBs are artificial. It means the signature is not inconsistent with artificial origin, and we should remain alert to patterns that might distinguish natural from artificial sources. The WOW signal, detected in 1977 by the Big Ear Radio Telescope, remains unexplained. It lasted 72 seconds, matched the expected signature of an extraterrestrial signal, and has never been detected again despite repeated observations of the same region of sky. The signal appeared to originate from the direction of constellation Sagittarius, though precise location could not be determined. Natural explanations involving hydrogen clouds or comet emissions have been proposed, but remain controversial. If civilizations occasionally transmit powerful signals, perhaps for purposes unrelated to communication, such as energy transfer or propulsion, we might detect them as one-time events that never repeat. The lack of repetition would be a feature, not bug. The civilization transmitted once, achieved its objective, and returned to silence. Dimming of cosmic background radiation in certain frequency ranges might indicate large-scale harvesting of stellar energy. If numerous Dyson spheres exist throughout the galaxy, the cumulative effect would be reduced visible light and increased infrared from waste heat. Surveys searching for this signature have found no strong candidates. But this might simply mean that civilizations harvest energy more efficiently than we assume, radiating waste heat in wavelengths difficult to detect or in directions away from Earth. Or perhaps they use energy at scales below detectability threshold. A civilization that achieves sustainability and limits growth might use only a small fraction of available stellar energy, making their presence nearly impossible to detect. Absence of evidence is itself a form of evidence under the right circumstances. The Fermi paradox is strengthened by every sky survey that finds nothing. Decades of SETI observations have covered millions of target stars across multiple wavelengths. We have detected no confirmed artificial signals. The more thoroughly we search without finding anything, the stronger the evidence that civilizations, if they exist, are not broadcasting. This is consistent with dark forest prediction. Advanced civilizations remain silent because silence equals survival. The universe is not empty, it is quiet. And quiet is maintained by selection pressure that eliminates the loud. But perhaps the most disturbing possibility is that we are detecting artificial phenomena and misinterpreting them as natural. How would we recognize alien technology if it operates on principles we do not understand? Clarke's third law states that any sufficiently advanced technology is indistinguishable from magic. Applied here, any sufficiently advanced technology might be indistinguishable from natural phenomena. If civilizations millions of years ahead of us harness physics we have not discovered, their activities might look like pulsars, gamma-ray bursts, or gravitational anomalies. We observe, we measure, we construct natural explanations, and we never realize we are looking at engineering. This is the planetarium hypothesis, proposed by philosopher Stephen Baxter. Perhaps advanced civilizations actively manage what we observe, showing us a sanitized version of the universe with all evidence of intelligence edited out, not through physical megastructures blocking our view, but through more subtle manipulation redirecting signals, masking signatures, or feeding false data into our instruments. This sounds paranoid, but consider, if civilizations wish to remain hidden from emerging species like us, the most reliable method is ensuring we cannot detect them. Passive concealment, simply not broadcasting, leaves a chance of accidental detection. Active concealment, actively managing what emerging civilizations observe, guarantees invisibility. We have no way to detect such manipulation if it exists. Our understanding of the universe is built entirely on observations. If those observations are curated, our understanding is false but internally consistent. We would construct cosmology, physics, and astronomy that accurately describe the curated data while missing the underlying reality. This is an unfalsifiable hypothesis. It cannot be tested because any test uses the potentially compromised observational base. But it illustrates the depth of the epistemic problem. We cannot trust that our observations represent reality if sufficiently advanced entities wish to deceive us. The most testable prediction of dark forest theory is continued silence. If the theory is correct, we should detect no unambiguous technosignatures regardless of how thoroughly we search. Every survey should return null results. Every anomaly should eventually receive natural explanation. The universe should appear empty of intelligence except for us, and this is exactly what we observe. The great silence persists. After 6 decades of SETI, 0 confirmed detections, the dark forest predicts precisely this outcome. The absence of evidence is evidence of concealment, and concealment implies something worth hiding from. The ethics of silence. Should humanity stop broadcasting? The dark forest theory presents a moral dilemma. Should humanity cease all deliberate transmission into space? This is not merely a technical question about communication protocols. It is a philosophical question about our responsibilities to future generations, our species' right to take risks on behalf of others, and whether survival justifies abandoning our curiosity about the cosmos. The debate has split the scientific community. Opponents of active SETI argue that deliberate transmission represents existential gambling without informed consent. The decision to broadcast affects billions of people, current and future generations, yet is made by small groups of researchers without democratic input or international oversight. Astrophysicist David Brin has been a vocal critic, arguing that active SETI violates the principle of prudence that should govern decisions with catastrophic downside risk. He points out that we are essentially conducting an experiment with only one Earth as a test subject. If the experiment goes wrong, there is no reset button. Extinction is permanent. This argument parallels debates about other existential risks. Nuclear weapons testing, genetic engineering of viruses, artificial intelligence development, all present scenarios where mistakes could be irreversible. Society has developed frameworks for managing such risks. Regulatory oversight, safety protocols, international agreements. But active SETI currently operates with no equivalent framework. Any organization with sufficient resources can transmit. No international treaty governs extraterrestrial messaging. The Outer Space Treaty of 1967 addresses property rights and weapons deployment, but does not mention communication. Absence of regulation means absence of accountability. Individual researchers can increase humanity's risk profile without constraint. The precautionary principle, widely accepted in environmental policy, states that when an activity raises threats of harm to the environment or human health, precautionary measures should be taken, even if some cause and effect relationships are not fully established scientifically. Applied to active SETI, the possibility that broadcasts might attract hostile attention, even if probability is uncertain, justifies restraint. We do not fully understand the risks. Therefore, we should err on the side of caution until we do. This does not mean never communicating. It means establishing protocols, conducting risk assessment, building consensus before transmitting. Proponents of active SETI counter that the risks are overblown and that humanity has already crossed the threshold. Television and radar signals have been propagating outward for nearly a century. If hostile aliens exist within 90 light-years, they can already detect us. Remaining silent now accomplishes nothing we have already revealed ourselves. Furthermore, they argue that contact with advanced civilizations, even if risky, might be humanity's only path to long-term survival. Perhaps they possess knowledge that could solve climate change, energy scarcity, or other existential threats we face. The risk of silence might be greater than the risk of transmission. This argument has flaws. First, passive leakage and deliberate transmission are not equivalent. Leakage is weak, diffuse, and requires extraordinary receiver sensitivity to detect. Deliberate transmission is strong, focused, and designed for detection. The difference in detectability is orders of magnitude. Second, the "we've already been detected" argument assumes detection is binary. Either they know about us or they do not. But detection might be gradual. Passive signals reveal biological activity and perhaps primitive technology. Active transmission reveals spacefaring ambitions and advanced capability. The threat assessment changes. Finally, the argument that contact might provide benefits assumes benevolence, or at least neutrality. Dark forest theory suggests this assumption is unjustified. A middle position proposes that humanity should engage in passive SETI, but refrain from active transmission until we better understand the risks. Continue listening. Continue scanning for signals, but do not broadcast. This listen but don't speak strategy allows us to gather information about the galactic environment without increasing our risk profile. If we detect signals from other civilizations, we can assess their content, their distribution, their characteristics, before deciding whether to respond. Information is valuable. Premature transmission surrenders information advantage. Some researchers argue that remaining silent is itself a gamble. If other civilizations are friendly or neutral, failure to communicate means missing opportunity for beneficial contact. The game theory works both ways. If most civilizations are peaceful, mutual silence creates mutual loss. Only by taking the risk of communication can we reap the benefits of the galactic community. But this argument requires assumptions about alien intentions that we have no basis for making. We are asked to gamble extinction against potential benefits when we cannot assess probabilities. That is not rational risk-taking. That is recklessness. The generational dimension complicates the ethics. Current humans alive today might benefit from contact if aliens are benevolent. But future humans, potentially trillions of individuals over millions of years, bear the consequences if aliens are hostile. Do we have the right to impose that risk on them? Democratic theory suggests that decisions affecting future generations require special consideration because those affected cannot consent. Many environmental policies explicitly incorporate intergenerational equity, the principle that current generations should not compromise the well-being of future ones. Applied here, we should not increase existential risk for humanity as a whole without a consensus mechanism that accounts for future interests. But achieving global consensus is impractical. Earth contains hundreds of nations with competing interests. International agreements require years of negotiation. Meanwhile, Technology for powerful transmission is widely available. Radio telescopes exist in dozens of countries. Anyone with sufficient funding and motivation can transmit. The tragedy of the commons emerges. Collective restraint benefits everyone, but individual defection is easy and often goes unpunished. One rogue transmission could trigger the very detection we collectively wish to avoid. How do you prevent unilateral action in a system with no enforcement mechanism? Some propose technical solutions. Perhaps we should focus on passive observation and internal cultural development rather than external communication. Perhaps we should encrypt our communications to make them indistinguishable from random noise to external observers. This is information hiding. Rather than simple silence, we continue using radio, television, and radar, but in ways that do not reveal intelligence to distant observers. Spread spectrum communications, for example, distribute signal power across wide frequency ranges, making detection difficult. Modern communications already trend toward lower power and more directionality. Our signals might naturally become less detectable as technology advances. But encryption cannot hide all signatures. Atmospheric composition remains detectable. Thermal signatures from industrial activity might become visible as we expand energy use. Radio leakage from poorly shielded electronics creates a noise floor that, while not structured signals, still represents artificial source. Complete concealment might be impossible once civilization reaches a certain technological level. Perhaps the dark forest requires not just communication silence, but technological restraint, deliberately limiting our growth to remain beneath detection thresholds. This raises different ethical questions. Do we have the right to limit humanity's potential, to reduce risk from hypothetical threats? The philosophical debate ultimately cannot be resolved without more information. We need to know whether hostile aliens exist, how common they are, and what detection capabilities they possess. But acquiring that information requires observation and potentially communication to the very actions under debate. We are trying to assess risk while blind. Every decision is made under profound uncertainty. In such situations, different ethical frameworks yield different recommendations. Consequentialism focused on outcomes might favor communication if expected benefits outweigh expected costs. Deontological ethics focused on duties and rights might oppose unilateral decisions affecting all humanity. Virtue ethics focused on character might emphasize prudence and humility in face of cosmic unknowns. What seems clear is that the current approach allowing arbitrary transmission without coordination or oversight is inadequate. At minimum, international discussion is warranted. Frameworks for risk assessment should be developed. Consensus-building mechanisms should be established. Even if perfect agreement is impossible, the conversation itself has value. It forces us to articulate our assumptions, our values, and our priorities as species. It makes explicit the trade-offs between curiosity and safety, between exploration and caution, and it prepares us, should contact occur, to respond thoughtfully rather than reactively. The dark forest theory does not provide a definitive answer about whether we should transmit. It provides a framework for thinking about risks. It suggests that assumptions of benevolence are unjustified. It demonstrates why caution might be an adaptive strategy. Whether that justifies silence is an ethical question that each person, each society must answer for themselves. But the question should be asked, and it should be asked now, before more powerful transmissions are sent, before detection becomes irrevocable, before our cosmic shout echoes so far that silence is no longer possible. The technological trajectory. Are we approaching the danger zone? Humanity's technological development follows an exponential curve. Each advancement enables faster subsequent advancement. Knowledge accumulates, capabilities compound. But this trajectory, while enabling enormous benefits, also increases our visibility and threat profile. We are entering the phase of development where we become simultaneously dangerous to others and vulnerable to attack. Understanding this trajectory is critical because it determines when broadcasting becomes most hazardous and when detection might trigger response. Current human civilization ranks approximately 0.72 on the Kardashev scale. We use about 0.7% of available planetary energy. Our radio signals have propagated 90 light-years, potentially alerting any listeners within that radius. Our space activities include satellites, space stations, and probes throughout the solar system. We possess nuclear weapons capable of destroying our own civilization, but insufficient energy-gathering infrastructure to threaten civilizations beyond Earth. Militarily, we are dangerous only to ourselves. But this is changing rapidly. Several technological developments within the next 50 to 100 years could dramatically alter our threat profile. Fusion power, if achieved, would provide access to vastly greater energy. Current fission reactors produce about 400 gigawatts globally. Fusion could scale to terawatt levels within decades of successful prototype. This energy could power directed energy weapons, particle accelerators, or propulsion systems capable of relativistic velocities. A civilization with fusion power can, in principle, build weapons threatening to other star systems. This moves us from dangerous only to self to potentially dangerous to neighbors. Self-replicating space-based manufacturing represents another threshold. If we develop von Neumann probes robots that can mine asteroids, refine materials, and construct copies of themselves, we gain exponential expansion capability. One probe becomes 2. 2 become 4. 4 become 8. Within decades, millions of probes could spread throughout the solar system and beyond. From an external perspective, this looks like preparation for expansion. An expanding civilization is a threatening civilization. Even if our intentions are purely peaceful, scientific exploration and resource gathering, others cannot verify this. Capability matters more than intention. Artificial superintelligence might be the most significant threshold. Current AI systems, like GPT-4 and other large language models, exhibit impressive capabilities, but remain narrow, good at specific tasks, lacking general intelligence. But progress is rapid. Many researchers predict artificial general intelligence, AGI, AI, matching human cognitive capability across all domains within 20 to 50 years. An AGI can analyze its own code, identify improvements, and implement them. Each iteration makes it smarter, enabling faster subsequent improvements. This feedback loop could progress from human level to superintelligent in days or months, an intelligence explosion. A superintelligent AI would be to human intelligence what human intelligence is to chimpanzees. It would solve problems we cannot comprehend, design technologies we cannot conceive, and potentially develop capabilities that violate our current understanding of physics. From the perspective of external observers, a civilization developing superintelligence is crossing the most dangerous threshold. An ASI could rapidly develop interstellar weapons, crack encrypted communications from other civilizations, or devise strategies for galactic dominance that no biological intelligence could anticipate. The moment we activate superintelligence, we transform from containable threat to existential hazard. Biotechnology presents yet another risk vector. CRISPR gene editing and synthetic biology are advancing rapidly. Within decades, we may possess the ability to design organisms from first principles, including pathogens optimized for lethality and transmission. A civilization with advanced biotechnology could theoretically engineer weapons targeting specific biochemistries. If Earth life uses DNA-RNA protein architecture similar to other life in the galaxy, our bioweapons might be dangerous to aliens as well. Even if we develop these technologies defensively, external observers cannot verify our intentions. The mere capability changes the threat calculation. These technological developments cluster temporally. We will likely achieve fusion, self-replicating probes, AGI, and advanced biotechnology within the same 1 to 2 century window. This is our vulnerable period, the window where we possess offensive capabilities sufficient to threaten others but lack defensive capabilities sufficient to protect ourselves. We become dangerous before we become secure. This is exactly when dark forest logic predicts we are most likely to be targeted. A preventive strike before we achieve truly dangerous capabilities is more effective than waiting until we have deployed those capabilities across the solar system or beyond. The trajectory is observable from outside. Our electromagnetic emissions reveal increasing technological sophistication. Television broadcasts in the 1950s showed primitive but advancing technology. Modern digital communications show rapid progress. If we suddenly achieve fusion, our energy signature changes dramatically. If we launch self-replicating probes, their activity becomes detectable. If we develop AGI and it begins making scientific breakthroughs, the pace of our advancement accelerates visibly. External observers can track our progress, estimate when we will cross dangerous thresholds, and calculate optimal intervention timing. Military strategists recognize this pattern. During the Cold War, both the United States and Soviet Union considered preventive war attacking before the enemy's nuclear arsenal became fully developed. The Cuban Missile Crisis represented precisely this calculation. The US considered military action to prevent Soviet missile deployment in Cuba because deployed missiles shifted the strategic balance. The same logic applies at interstellar scale. If you detect a civilization developing dangerous capabilities, you face a choice: strike now while they are vulnerable, or wait until they are too powerful to stop. Rational actors choose the former. This creates what international relations scholars call the security dilemma. Actions taken to increase your security, developing weapons, building defenses, expanding capabilities, decrease others' security, prompting them to do the same. The result is an arms race, where everyone becomes less secure, despite everyone's efforts to become more secure. At interstellar scale, this dilemma is more severe because verification is impossible. You cannot inspect alien weapons programs. You cannot enforce treaties across light years. You cannot trust assurances of peaceful intent because you cannot verify them. Our current trajectory amplifies this problem. We are not merely developing these technologies, we are broadcasting our progress. Scientific papers describe our achievements. Television and internet traffic leak into space. Military radar systems transmit at high power. We are simultaneously becoming more dangerous and more visible. This is the worst possible combination. If we were developing quietly, we might become capable before being noticed. If we were visible but non-threatening, we might be ignored. But visible and increasingly threatening triggers exactly the response dark forest theory predicts. Some researchers argue that our trajectory will naturally lead to quieter technologies. Modern communications use lower power and more directionality than older systems. Fiber optics and cable networks contain signals rather than broadcasting them. Satellite communications use spot beams rather than omnidirectional transmission. Perhaps our electromagnetic signature will actually decrease as technology matures, making us less detectable even as we become more capable. This is an optimistic scenario. We become dangerous quietly, cross the vulnerability threshold undetected, and achieve security before anyone notices us. But other signatures may betray us. Atmospheric composition changes as industry expands. Artificial greenhouse gases, like chlorofluorocarbons, have no natural sources and persist for decades. Industrial pollutants create spectroscopic signatures detectable through exoplanet atmospheric analysis. Even if we eliminate electromagnetic leakage, our planetary chemistry reveals technological civilization. And, unlike radio signals that propagate at specific frequencies allowing selective listening, atmospheric signatures are visible to anyone doing systematic exoplanet surveys, a common scientific activity for civilizations searching for habitable worlds. The trajectory also affects when response becomes feasible. A civilization 50 light-years away receives our signals 50 years after transmission. If they immediately launch relativistic weapons, those arrive 55 years after our original transmission. Total, 105 years from signal to impact. For humanity, this means transmissions from the 1920 onward might trigger responses arriving between 2025 and 2100. We are entering the window where consequences of early broadcasts could manifest. If dark forest logic governs galactic politics, the next few decades are critical. This timing creates cruel irony. The period when we understand the risks now is too late to prevent exposure from early broadcasts. But it is not too late to avoid amplifying that exposure with continued deliberate transmissions. We cannot undo the past, but we can avoid making the situation worse. Yet many in the scientific community continue advocating for more powerful, more frequent broadcasts, precisely when we should be most cautious. The disconnect between risk awareness and risk management is troubling. The question is whether alternative trajectories exist. Could humanity develop differently, achieving security before becoming visible, or achieving capability without triggering threat perception? This requires intentional choice. It means prioritizing stealth over openness, caution over exploration, survival over curiosity. It means accepting that we might remain isolated for centuries or millennia until we achieve capability sufficient to defend ourselves. It means fundamentally restructuring our approach to technology development, communication policy, and space exploration. Whether this is possible or desirable remains an open question. Human nature includes curiosity, expansionism, and risk-taking. These traits enabled our evolutionary success. They drove us from Africa to every continent. They pushed us to explore space despite enormous costs and dangers. Asking humanity to suppress these instincts for centuries requires cultural transformation unprecedented in our history. Perhaps it is impossible. Perhaps we are locked into a trajectory that ends either in extinction or transformation into type silent civilization through painful lessons. Perhaps the dark forest selects against species that cannot learn caution, and perhaps we are about to discover whether we can learn in time. The silent strategy. What hiding actually requires. If the dark forest theory is correct and survival requires concealment, what specifically would humanity need to do? This is not a simple matter of turning off transmitters. True stealth at interstellar scale requires a comprehensive approach addressing every way our civilization might be detected. The requirements are technically challenging and socially disruptive. Understanding these requirements reveals why achieving type silent status represents immense undertaking, and why civilizations that succeed might be fundamentally different from us. First requirement: eliminate electromagnetic emissions. All radio, television, radar, and microwave transmissions must either cease or be contained. This means abandoning broadcast communications in favor of directed beams, fiber optics, and cable systems. Current infrastructure would require massive overhaul. Broadcast radio and television stations worldwide number in the tens of thousands. Each radiates kilowatts to megawatts into space. Replacing this with purely terrestrial communications infrastructure would cost trillions of dollars and require decades. Some applications, aircraft navigation, weather, radar, satellite communications, have no obvious alternatives. New technologies would need to be developed. Military radar represents a particular challenge. Over the horizon, radar systems transmit at megawatt levels to bounce signals off the ionosphere and detect aircraft or missiles thousands of miles away. Planetary defense systems scanning for asteroids transmit powerful pulses into space. Eliminating these systems compromises national security and planetary safety. Alternatives exist: space-based optical telescopes for asteroid tracking, different military surveillance methods, but implementation requires international cooperation and substantial investment. Nations would need to coordinate, which requires trust that currently does not exist. Second requirement: manage atmospheric signatures. Industrial processes produce gases that do not occur naturally. CFCs, SF6, nitrogen trifluoride, and other synthetic compounds have distinctive spectroscopic signatures visible to exoplanet atmospheric analysis. Eliminating these requires either ceasing the industrial processes that produce them or developing capture technologies preventing release. This affects semiconductor manufacturing, refrigeration, electrical equipment, and numerous other industries. The economic cost would be substantial. Developing nations would bear a disproportionate burden. Enforcement would require a global monitoring regime. Natural atmospheric signatures also matter. Oxygen concentration at Earth's level does not occur without photosynthetic life. This cannot be hidden without geoengineering on planetary scale, perhaps introducing chemicals that mask oxygen signatures or creating artificial atmospheric composition indistinguishable from lifeless worlds. Both options are technologically infeasible with current capabilities and would have unknown ecological consequences. If atmospheric biosignatures trigger detection, we cannot conceal ourselves without either abandoning technological civilization or leaving Earth. Third requirement: constrain energy use and heat signature. All energy use generates waste heat. At current levels, Earth's waste heat is undetectable at interstellar distances. But if civilization continues expanding energy use at historical rates, roughly 2 to 3% annually, within a few centuries, our thermal signature becomes noticeable. Advanced civilizations might detect temperature anomalies indicating industrial activity. Achieving sustainability plateau where energy use stabilizes at undetectable levels requires abandoning the growth paradigm that defines modern economies. This implies a steady-state economy concept theoretically sound, but never successfully implemented at large scale. Fourth requirement: control space activities. Self-replicating probes spreading through the solar system would be visible to nearby observers. Mining asteroids at industrial scale generates dust, changes orbits, and creates thermal signatures. Dyson spheres or orbital habitats at sufficient scale alter the star's light curve. Space activities must remain below the detection threshold. This means either extremely limited space presence, small satellites, minimal infrastructure, or developing stealth technologies that render space activities invisible. The latter might be possible. Low albedo materials, thermal management preventing infrared leakage, trajectories avoiding detection geometries, But it requires deliberate design, prioritizing concealment over efficiency. Fifth requirement, social discipline. Every human with access to a powerful transmitter becomes a potential defector. One rogue transmission could reveal our presence regardless of official policy. This requires either global surveillance, preventing unauthorized broadcasts, or societal consensus so strong that individuals self-police. Neither is currently achievable. We cannot monitor every radio transmitter on Earth. We cannot prevent individuals from building new transmitters. We cannot enforce electromagnetic silence without authoritarian control mechanisms most societies would reject. Perhaps future technologies enable this AI monitoring all electromagnetic emissions, automatically suppressing unauthorized signals. But that raises questions about freedom, privacy, and the kind of society we become. These requirements reveal why achieving type silent status is not merely a technical problem, but civilizational transformation. The society that successfully hides from galactic observers would look radically different from current human civilization. It would prioritize security over growth, caution over exploration, concealment over communication. It would accept constraints on individual freedom to enforce collective safety. It would maintain technological stagnation or very slow advancement to avoid crossing detection thresholds. It would be, in many ways, the opposite of everything that drove human progress for the past few centuries. This raises a disturbing question. Are the only civilizations that survive those willing to fundamentally alter their nature? Does the dark forest select for specific cultural traits caution, discipline, authoritarianism, stagnation? If so, the galaxy might be full of civilizations that have survived precisely by becoming something we would not recognize as free societies. They exist, but they exist in stasis, maintaining minimal profile, never expanding beyond their home systems, never taking risks. They survive, but at the cost of everything that makes existence interesting. Alternative interpretation is more optimistic. Perhaps achieving type silent status requires technological advancement so extreme that detection becomes impossible through mastery rather than restraint. A civilization that achieves complete understanding of physics might manipulate space-time in ways we cannot imagine, hiding in dimensions we do not perceive, communicating through channels we cannot detect. They are not constrained by silence. They have transcended the need for primitive electromagnetic communications. They are everywhere but invisible because our instruments are too crude to detect them. This latter interpretation suggests that achieving true stealth requires passing through the vulnerability period first. Young civilizations like ours lack the technology to hide effectively. We can reduce our signature but not eliminate it. Only after achieving certain technological thresholds, perhaps control of fundamental forces, mastery of quantum entanglement, or access to physics beyond standard model, can civilizations truly disappear. Until then, we are in a danger zone, visible enough to be detected, capable enough to be threatening, but not advanced enough to defend ourselves or hide completely. Current human trajectory does not prioritize stealth. We are expanding electromagnetic emissions through growing communications infrastructure. We are increasing energy use through economic growth. We are planning space expansion through asteroid mining and off-world colonies. We are developing precisely the technologies, AI, fusion, biotech, that make us most threatening. And we are doing all of this while broadcasting our progress. We are following the loudest possible development path through the most dangerous phase of civilizational evolution. If dark forest theory is correct, this is suicidal trajectory. Changing course requires collective decisions unprecedented in human history. It requires nations to cooperate despite competing interests. It requires individuals to accept constraints on freedom for collective security. It requires industries to abandon profitable activities. It requires scientists to withhold discoveries. It requires species-level coordination on timescales exceeding individual human lifespans. Whether humanity is capable of this remains unknown. We have never attempted anything comparable. We have no institutional mechanisms for such coordination. We have no cultural traditions supporting multi-generational sacrifice for abstract future benefits. This might be the real great filter. Not technological self-destruction through nuclear war or climate change. Not biological barriers like abiogenesis or eukaryotic evolution. But social-political inability to coordinate response to existential threat when that threat is probabilistic, distant, and abstract. We can respond to immediate dangers we built, bomb shelters during the Cold War, we implemented environmental regulations after visible pollution, but can we respond to danger that might not manifest for decades or centuries? Can we sacrifice current benefits for future security when the threat remains theoretical? History suggests we cannot. Every long-term collective action problem, climate change, nuclear proliferation, pandemic preparedness, demonstrates our inability to coordinate effectively across time and space. If this is the filter, then perhaps the Great Silence is explained not by hostile aliens eliminating broadcasting civilizations, but by civilizations self-destructing through inability to achieve the coordination necessary for survival. The dark forest exists not because predators hunt, but because prey cannot organize. The galaxy is full of ruins, not because civilizations were destroyed from outside, but because they destroyed themselves through failure to cooperate. And we are following the same path, broadcasting our presence while failing to develop the social technologies necessary for our own survival. Contact protocols. If they are out there, what happens next? Despite all precautions, despite arguments for silence, contact might occur. We might detect their signal, they might detect ours. Or we might encounter their probes, their artifacts, or them directly. What happens then? How should humanity respond? The answers determine whether first contact becomes an extinction event or something else, and we are remarkably unprepared. Currently, no international treaty governs response to extraterrestrial contact. The United Nations Committee on the Peaceful Uses of Outer Space has no binding protocols. NASA has internal procedures, but no authority over other nations or private entities. The Declaration of Principles concerning activities following the detection of extraterrestrial intelligence, drafted by the SETI Committee of the International Academy of Astronautics in 1989, is a non-binding statement of intent, not enforceable policy. It suggests that discoverers should verify the signal, notify relevant authorities, and avoid transmitting responses without international consultation. But it has no enforcement mechanism, and most nations have not officially endorsed it. The detection scenario poses immediate challenges. Suppose a radio telescope detects artificial signals from a star 50 light-years away. The first question, is it real? False positives are common interference from satellites, radar systems, or terrestrial sources, mimics extraterrestrial signals. The WOW signal was never confirmed despite repeated observations. Verification requires multiple independent detections using different instruments at different locations. This takes time, days to weeks. During this period, the information might leak. Astronomical communities are interconnected. Rumors spread. Media reports appear before official confirmation. Once verified, the next question: who decides response? The discoverers? Their government? United Nations? Humanity as a whole? Each option has problems. Discoverers are scientists without political authority. Governments represent national interests that might not align with collective human interest. United Nations lacks enforcement capability and moves slowly. Democratic global referendum is impractical. By the time consensus emerges, others might have already responded. The tragedy of the commons again. Everyone benefits from coordinated response, but individual actors face incentives to defect. The content of any response is even more problematic. What do we say? The Arecibo message contained mathematics, chemistry, biology, and information about Earth. But this reveals capabilities, location, and vulnerabilities. Dark forest logic suggests revealing anything is dangerous. Even simple acknowledgement, "We received your message," confirms our existence and provides updated information about our technological level. Perhaps the optimal response is no response. Monitor the signal. Learn everything possible, but maintain silence. But silence has costs. If the signal is an invitation to mutual cooperation, ignoring it wastes opportunity. If the senders are benevolent and merely curious, silence appears hostile or primitive. If other civilizations respond while we remain silent, we lose the chance to shape the conversation. Game theory of response is complex. If a signal comes from a peaceful civilization, responding enables cooperation. If a signal comes from hostile civilization, testing for responses, silence protects us. Without knowing their intentions, which we cannot, optimal strategy is ambiguous. The ambiguity extends to interpreting the signal itself. What if the message is a warning? Do not transmit. Danger exists. Do we trust it? Perhaps it is a genuine warning from benevolent civilization. Perhaps it is deception meant to keep us silent while they prepare an attack. Perhaps it is a test of our judgment. We cannot know. Every possibility has a different optimal response, and we must choose under time pressure, incomplete information, and with stakes, including human extinction. Physical contact scenarios are even more challenging. Suppose we detect an approaching object, spacecraft, probe, or artifact. What do we do? Military forces might perceive it as a threat and attack. The scientific community might want to observe and study. The public might panic or celebrate. Coordinating response when something visible is approaching is nearly impossible given current international relations. Different nations have different defensive capabilities, different political systems, and different cultural attitudes toward the unknown. Agreement on whether to welcome, ignore, or destroy an approaching object might be unachievable. The arrival scenario from the dark forest perspective is particularly grim. If theory is correct, we would not detect the approach until very late. Relativistic weapons would arrive with minimal warning. Self-replicating probes designed for stealth would reveal themselves only when ready to act. First contact might be last contact weapons detonating in the atmosphere, engineered pathogens released globally, or electromagnetic pulse disabling all electronics simultaneously. We would have minutes to hours between detection and extinction. No time for response, no chance for negotiation, just sudden, irreversible destruction. This scenario is why some researchers advocate for defensive preparations despite their apparent futility. If relativistic weapons can be launched, they likely cannot be intercepted. They move too fast, carry too much energy. But perhaps early warning systems could provide hours instead of minutes. Perhaps distributed backup systems could preserve human knowledge even if civilization falls. Perhaps off-world colonies could survive planetary strikes. These preparations seem paranoid, until you consider the cost of being unprepared when threat materializes is extinction. The cost of preparing against a threat that never materializes is wasted resources. Expected utility calculation favors preparation even if probability is low. But preparation reveals presence. Building planetary defense systems, launching monitoring satellites, establishing off-world colonies, all increase our detectability. Military preparations generate electromagnetic signatures. Space activities are visible. The very act of defending against potential threats makes us more visible to that threat. This is a security dilemma at a cosmic scale. Preparations meant to increase security instead increase danger. Perhaps the only winning move is not to play remain invisible, accept vulnerability, to hope we are not noticed. Some scenarios offer hope. Perhaps advanced civilizations have ethics prohibiting preemptive strike against species that have not demonstrated hostility. Perhaps the galactic community exists with laws, enforcement, and protection for emerging civilizations. Perhaps the dark forest logic is wrong, and most civilizations are peaceful. If so, contact could be humanity's greatest achievement, access to knowledge, technology, art, and philosophy accumulated across millions of years and thousands of civilizations. The potential benefits are unlimited. The risk is also unlimited. We gamble everything on assumptions about alien psychology we cannot verify. The most likely scenario might be neither apocalyptic destruction nor beneficial cooperation, but something stranger. Contact with intelligence so different from us that meaningful interaction is impossible. They communicate in ways we cannot comprehend. They perceive reality through sensory systems unrelated to ours. They value things we cannot imagine. Contact occurs but yields no understanding. We detect them, they detect us. Both parties recognize the other as intelligent, but communication breaks down because we lack common ground. This would be frustrating but not dangerous, assuming their incomprehension does not trigger threat response. The ethical dimension remains unresolved. Even if contact is dangerous, do we have the right to hide from the cosmos? Curiosity is fundamental to what makes us human. Exploration drove our species across continents, oceans, and into space. Abandoning that drive to huddle in darkness might preserve our bodies, but kill our spirit. Perhaps being human means accepting risk rather than choosing safety. Perhaps species that prioritize survival over everything else are not species worth preserving. This is a philosophical question without a definitive answer. What is clear is that we are unprepared for any contact scenario. We have no global institutions capable of rapid, coordinated response. We have no protocols that account for dark forest possibilities. We have no plans for scenarios where first contact is hostile. We have no defensive capabilities against relativistic weapons or other exotic threats. We are simultaneously broadcasting our presence and failing to prepare for consequences. This combination, visibility without preparation, might be the most dangerous position possible. We have announced ourselves to potential predators while remaining vulnerable to attack. If the dark forest is real, we have made every possible mistake, and we are running out of time to correct them. The stellar geography of risk, mapping our dangerous neighborhood. The dark forest theory translates into concrete geographic risk based on our location within the galaxy and the distribution of stars around us. Our position in the Milky Way, the density of nearby stellar systems, and the characteristics of those systems all contribute to our exposure profile. Understanding this stellar geography reveals which civilizations might already know about us, which pose the greatest threat, and whether our location offers any strategic advantages. Earth orbits a G-type main sequence star located approximately 26,000 light-years from the galactic center. We reside in the Orion Arm, a minor spiral arm between the larger Perseus and Sagittarius arms. This placement is neither central nor peripheral. We occupy what astronomers call the galactic habitable zone, a region where stellar metallicity suffices for planet formation, but supernova frequency remains low enough that sterilizing radiation events are rare. This zone, extending from roughly 23,000 to 30,000 light-years from the galactic center, represents the most likely region for technological civilizations to emerge. Within 100 light-years of Earth, approximately 14,600 star systems exist. These represent our immediate neighborhood, the volume within which our earliest radio transmissions from the 1920 have now propagated. Any civilization in this sphere with sufficiently sensitive receivers could have detected our signals. The nearest star, Proxima Centauri, lies 4.24 light-years away, hosting at least 2 confirmed planets, including one in the habitable zone. If technological civilization existed there, they received our radio signals around 1928, and their response could arrive as early as 1936. The absence of detected response suggests either no civilization exists, they remain silent deliberately, or their response has not yet arrived. Within 50 light-years, the distance our television broadcasts have propagated, approximately 2,000 stellar systems exist. Tau Ceti, 11.9 light-years away, is a G-type star with at least 4 confirmed planets. Its similarity to our Sun makes it a frequent Ceti target. If civilization exists at Tau Ceti, they have been receiving our broadcasts since approximately 1948. Response time would be 24 years total. We are now well past the window where we might expect response to early television broadcasts. Epsilon Eridani, 10.5 light-years distant, presents another promising candidate. This K-type star hosts at least 1 confirmed planet and possibly multiple worlds. Being younger than the Sun, approximately 800 million years old compared to 4.6 billion, it may not have had sufficient time for complex life to evolve. But if technological civilization can arise faster than it did on Earth, Epsilon Eridani could host observers who have detected us. The stellar density around our solar system is relatively low compared to the galactic average. In the dense central regions of the galaxy, stars are separated by as little as 0.1 light-years. In globular clusters, stars can be separated by mere light weeks. If dark forest logic applies, these dense regions are extraordinarily dangerous. A single transmission in a globular cluster might be detected by thousands of civilizations simultaneously. The probability of at least one being hostile approaches certainty. Our relatively isolated position might be a strategic advantage. Low stellar density means fewer potential observers. The nearest 1,000 stars are distributed across a volume of space roughly 70 light-years in radius. In the galactic center, the same number of stars would fit within 10 light-years. Our loneliness might be exactly what has allowed us to survive this long. We broadcast carelessly because few are nearby to hear, but isolation has limits. The observable universe contains approximately 100 billion galaxies, each with hundreds of billions of stars. Even if only 1 in a million stars hosts technological civilization, millions exist within our galaxy alone. The Breakthrough Listen project, launched in 2015, is surveying 1 million nearby stars for technosignatures. So far, 0 confirmed detections. This absence is itself a data point. Either civilizations are extraordinarily rare, or they are silent. Dark forest theory predicts the latter. Statistical analysis suggests that approximately 40 billion Earth-sized planets orbit in habitable zones of Sun-like stars in the Milky Way. If even 0.01% develop technological civilizations, 4 million exist. Distributed across the galaxy's volume, average separation between civilizations would be roughly 1,350 light-years. This is far enough that direct observation of planets is currently impossible. But radio signals are detectable at such distances with sufficiently large receivers. If civilizations 1,350 light-years away are listening, they receive signals from Earth's early radio era around 675 CE. Their response arrives around 4050 CE. This timing is critical. If the average distance to the nearest civilization is roughly 1,000 light-years, then responses to humanity's earliest broadcasts will not arrive until the next millennium. We are currently in a waiting period where consequences of our transmissions are still in flight. The weapons, if any, were launched, are en route but not yet detectable. The dark forest might appear empty not because it is, but because we have not yet waited long enough for the forest to react to our shout. The dark forest becomes less hypothetical and more geographical when viewed this way. We occupy a specific, mappable region surrounded by specific, innumerable stellar systems, each potentially hosting observers. Our broadcasts have created an expanding sphere of detection, currently 100 light-years in radius, encompassing 14,600 star systems. Within 50 years, that sphere will expand to 150 light-years, encompassing approximately 50,000 systems. Within a century, 100,000 systems. Each expansion multiplies our exposure. Each new star system represents another lottery ticket where we gamble that no hostile observer exists. The more tickets we draw, the greater the probability that eventually we lose. The weaponization of physics. How advanced civilizations could strike. The dark forest theory requires that advanced civilizations possess means to eliminate threats across interstellar distances. This is not science fiction speculation. It is applied physics. Multiple weapons concepts exist that are consistent with known physics and could be constructed by civilizations only modestly more advanced than humanity. Understanding these capabilities reveals why detection might equal death, and why the galaxy's silence might reflect rational fear rather than empty space. Relativistic kinetic weapons represent the most straightforward threat. The kinetic energy of an object equals 1/2 its mass times velocity squared. At relativistic speeds approaching light speed, relativistic corrections apply, but the fundamental principle remains: faster equals more energetic. A 1 kilogram projectile traveling at 90% light speed carries kinetic energy of approximately 10 to the power of 21 joules, roughly 250 megatons of TNT, 5 times the yield of the largest nuclear weapon ever tested. Accelerating mass to relativistic speeds requires enormous energy. Using conventional rocket propulsion is impractical. The rocket equation demands exponentially increasing fuel mass as velocity increases. But several alternative methods are theoretically viable. Particle accelerators demonstrate that accelerating small particles to near light speed is possible. CERN's Large Hadron Collider accelerates protons to 99.9999991% light speed. Scaling this to macroscopic objects requires more energy, but no new physics. A civilization with access to stellar-level energy output could construct electromagnetic launchers kilometers long, accelerating payloads to 0 to 9C or higher. Laser-pushed light sails offer another acceleration method. Powerful lasers directed at reflective sails can accelerate payloads efficiently. The Breakthrough Starshot initiative proposes using Earth-based lasers to accelerate gram-scale probes to 20% light speed for interstellar missions. A civilization with gigawatt-class lasers in space could scale this concept to accelerate larger payloads to higher velocities. The payloads need not be sophisticated, simple, dense masses like tungsten or iron suffice. Intelligence is not required, just mass and velocity. The targeting problem is manageable. Planets orbit predictably. Given knowledge of a planetary system's configuration and orbital parameters, calculating where Earth will be decades or centuries in the future is straightforward celestial mechanics. Aiming errors decrease with longer acceleration times. The projectile requires minimal guidance, perhaps none. Simply point it at where the target will be when the projectile arrives and releases. Detection and interception are nearly impossible. At 90% light speed, the projectile travels 1 light-year per 1.11 years. But the projectile is difficult to see. It might be black or covered in radar-absorbing material. It emits no propulsion signature because it is coasting. By the time radar confirms its presence, the projectile is already arriving at 0 Torn 9 C. Even 1 light minute of warning means the object closes approximately 16 million kilometers before detection. That leaves hours at most before impact. Not enough time to evacuate. Not enough time to intercept. Just enough time to know you are dead. Directed energy weapons present another threat vector. Sufficiently powerful lasers or particle beams could cause damage across interstellar distances. The challenge is focusing energy across light years. Diffraction causes beam spread proportional to distance and wavelength, inversely proportional to aperture size. But large apertures are possible. A phased array of lasers distributed across hundreds or thousands of kilometers and phase-locked could create effective aperture measured in hundreds of kilometers. Such systems could deliver destructive energy to planetary surfaces across light-year distances. The target need not be military infrastructure. Biosphere disruption is more effective. A sufficiently powerful laser tuned to wavelengths absorbed by atmospheric gases could trigger runaway greenhouse effect. Over months or years of continuous irradiation, atmospheric chemistry changes, temperatures rise, ecosystems collapse. The attacking civilization need not destroy the planet, merely render it uninhabitable. The indigenous species dies from environmental collapse, and the planet eventually becomes available for colonization. Biological weapons, optimized for interstellar deployment, might be even more insidious. Self-replicating probes could carry frozen microorganisms designed to activate upon atmospheric entry. These organisms need not be directly pathogenic. They could be terraforming agents designed to alter atmospheric composition or disrupt ecosystems. Released from orbit, they disperse globally. Indigenous species have no immunity. Collapse follows. Stellar engineering provides another category of weapon. A sufficiently advanced civilization might manipulate stars themselves, triggering premature stellar eruptions or inducing instabilities that increase harmful radiation, could sterilize planets across an entire stellar system. This requires capabilities well beyond current human technology, but not beyond theoretical physics. Stars are stable plasma balls maintained by balance between gravitational collapse and radiation pressure. Disrupting this balance could shift stellar output in ways lethal to life. These weapons share common features. They work across interstellar distances. They require no exotic physics. They are difficult or impossible to defend against. And they are within reach of civilizations moderately more advanced than humanity. We are perhaps centuries from building relativistic kinetic weapons. We understand the physics of directed energy and stellar manipulation even if we cannot yet engineer them. Any civilization 1,000 years ahead of us likely can. Any civilization 1,000,000 years ahead definitely can. The strategic calculus is clear. If you detect a potential threat and possess weapons capable of eliminating that threat from a safe distance, and if elimination costs less than risk of future conflict, then the rational choice is to strike preemptively. The target receives no warning. Years or decades or centuries later, the weapons arrive. Civilization ends. The attackers remain hidden, having eliminated one potential competitor. This is the dark forest, and we are shouting into it, oblivious to the predators who might already be taking aim. The Fermi paradox solutions. Why every answer points to danger. The Fermi paradox has generated dozens of proposed solutions since Enrico Fermi first articulated it in 1950. Each attempts to explain the contradiction between high probability of extraterrestrial intelligence and the complete absence of evidence. What is remarkable is that most solutions, when examined carefully, either support the dark forest theory or fail to adequately address it. The paradox may not be paradox at all, but rather confirmation that silence equals survival. The temporal explanation suggests we are simply early. Perhaps technological civilizations are rare because the universe has only recently become old enough for them to emerge. Earth formed 4.5 billion years after the Big Bang, roughly 1/3 the universe's current age. The first generation of stars contained almost no heavy elements necessary for planet formation. Perhaps the window for technological civilizations only opened relatively recently on cosmic timescales. This explanation seems reasonable until you consider the numbers. Even if intelligent life only emerges in the last 10% of the universe's history, the most recent 1.4 billion years, that still provides ample time for civilizations to arise, expand, and become detectable. A civilization that achieved interstellar travel just 10 million years ago would have had time to colonize a significant portion of the galaxy. The Milky Way is approximately 100,000 light years across. Even traveling at modest 1% light speed, expansion crosses the galaxy in 10 million years. Where are their colonies? Where is their infrastructure? The temporal explanation fails unless we assume humanity is extraordinarily, implausibly early first or among the first civilizations to emerge. The Great Filter hypothesis offers more concerning explanation. If some evolutionary step between a sterile planet and a spacefaring civilization is extraordinarily difficult, then the number of civilizations that successfully complete all necessary steps is small. The critical question is, where is the filter? Behind us or ahead of us? If behind us, if our biogenesis or intelligence is the bottleneck, then we are rare but safe. But if the filter lies ahead, if civilizations routinely destroy themselves before achieving interstellar capability, then we are in danger. Consider, we have existed as a technological civilization for approximately 100 years. We have possessed extinction-level weapons for 80 years. We came close to nuclear war multiple times. We are now developing other extinction risks: climate change, engineered pandemics, artificial intelligence. We have not yet achieved sustainable interstellar presence. The window between developing dangerous technologies and achieving resilience through interstellar distribution is narrow. Perhaps most civilizations fail to navigate this window. The galaxy is silent because the cemetery is quiet. This explanation is consistent with dark forest theory. Civilizations that survive are those that successfully navigate the danger window and learn caution. They become silent because broadcasting during the vulnerable phase invites elimination. They remain hidden after achieving security, because hiding is the strategy that works. The galaxy is full of civilizations, but all are silent survivors. The loud ones are all dead. We are loud. Therefore, we are at risk. The zoo hypothesis proposes that advanced civilizations exist, but deliberately avoid contact with primitive species, like humanity. But why would all civilizations agree to this? The zoo hypothesis requires coordination across multiple independent species with potentially different values and strategic interests. This seems implausible unless there is an enforcement mechanism, and enforcement requires detectable infrastructure. We see neither. The dark forest provides a more parsimonious explanation. Civilizations avoid contact not from ethics, but from self-preservation. Each independently concludes that revealing themselves is dangerous. No coordination is necessary. Simple survival instinct leads each civilization to silence. The apparent zoo is not managed preserve, but a natural outcome of universal caution. We are not being protected. We are being ignored or monitored while observers wait to see if we destroy ourselves. The transcension hypothesis suggests advanced civilizations lose interest in physical expansion. They retreat into virtual reality or otherwise transcend physical existence. This explains the absence of expanding empires, but not absence of signals. Even civilizations that transcend presumably pass through technological phases. During that phase, they broadcast. We should detect signals from thousands of civilizations at various stages. We detect none. Unless transcension happens extremely quickly, civilizations broadcast for only decades before transcending. This hypothesis fails to explain the silence. Moreover, transcension does not eliminate dark forest concerns. Even virtual civilizations require physical infrastructure, computing substrates, energy sources, cooling systems. This infrastructure might be targeted. A civilization that transcends but fails to hide remains vulnerable. Perhaps transcension is adaptation civilizations retreat into non-physical existence, specifically to become undetectable. But this is simply another form of hiding, consistent with dark forest logic. The "they are already here" explanation suggests aliens are present but undetected. Perhaps they exist as probes in the solar system, observing us silently. This is an unfalsifiable hypothesis. If they are perfect at hiding, we will never detect them. But it is also consistent with dark forest theory. Self-replicating probes spreading throughout the galaxy would be an optimal strategy for monitoring potential threats. They observe every star system, identify emerging civilizations, and report back. If such probes exist around Earth, we are already detected. And if we are detected, the observers are assessing us. Are we a threat? Should we be eliminated? The decision might already be made. The weapons might already be in flight. Every attempted solution to the Fermi paradox either fails to explain the evidence or supports the conclusion that silence is strategic. The temporal explanation requires implausible assumptions. The Great Filter suggests we face existential risks ahead. The zoo hypothesis requires coordination that would be detectable. Transcension requires implausibly rapid transition. "They are here" is unfalsifiable, but terrifying if true. Only the dark forest explains all observations. The silence, the absence of megastructures, the lack of expansion, the failure of SETI. It predicts exactly what we observe. A galaxy that appears empty but might be full of hidden observers, each watching the others, each waiting for someone else to make a fatal mistake. Each maintaining silence because silence is what survivors do. And we are breaking that silence loudly, continuously, for a century. In a forest full of predators, we are the ones making noise. and predators are patient.